I'm a CCS chemistry major here at UCSB. I work in the Reed Deolani group alongside Emory DeSec-EC, and I've been funded through the MARC program, where I assist with research into modifying the chain ends of wrapped polymers. And what this generally looks like is taking a polymer, which is just a long chain of repeating units, and adding a bromine to the end. And this is done because bromine is often used in syntheses because it is so easy to exchange for other functional groups. So therefore, by putting it on the end of your polymer, you make further modifications much easier. And you can now tailor these chain ends to whatever your application is. And that spans a variety of applications. And just one example is block copolymers. And this is an ATRP initiator here. And ATRP is just another type of polymerization, and an initiator is what starts the reaction. But you'll notice that it contains a bromine, and your polymer now would contain a bromine. So therefore, you could grow another separate chain off of your existing polymer and make blocks of polymers. And these are used in things from adhesives and rubbers to the biomedical field. And one example is micelles. So if you make part of your polymer hydrophobic, the other hydrophilic, in an aqueous environment such as the body, the hydrophobic parts will come together and the hydrophilic parts will make a shell, and you can deliver things into the body like that. But I specifically work with what are called wrapped polymers. And these are reversible addition, fragmentation, chain transfer polymers. But this is just a long phrase that describes the mechanism that wrapped polymers undergo. But what I'd like you to know is that they are a type of controlled radical polymerization, which means that they have control of the molecular weights. And if you notice, in traditional radical polymerizations, the chain lengths are inconsistent, which means your molecular weights span a much more broad range, and you get a distribution that is much wider. Whereas in wrapped polymerization, you get chain lengths that are very consistent in size, so the molecular weights tend to span a much narrower region, and you get a narrow distribution as shown here. And this is called, in the polymer world, it's called a narrow polydispersity. And these are all desired characteristics. However, there are other types of controlled radical polymerizations, so why specifically wrapped? And it is because of the versatility that wrapped provides. And this versatility comes because wrapped has a very large tolerance for functional groups in the monomers, the solvents, and the initiators, as well as you can make a variety of complex architectures, such as the star shown here, the worm shown here, and the dendrimer. You can also push these to high conversions, and this all together, you can tailor your polymers to be water soluble, which makes wrapped one of the most useful polymerization techniques in the biomedical field. And just one example is this protein is being functionalized with a wrapped block copolymer. But wrapped does have its challenges, and these challenges are rooted in what is called the chain transfer agent. And this is because this carbon-sulfur bond here is extremely weak, and this double bond here is reactive. And this is necessary for propagation to make the polymers. However, once it is on your chain end, it still retains these reactive qualities. So this leads to conjugation, which ultimately leads to discoloration, often yellow, which may be an undesirable characteristic if this is to be used in commercial products. However, it also can decompose quite readily, leading to poor retention of the chain end. And so when these decompose and come off, there can be odors, since thiol-containing compounds can be extremely smelly. They can also lead to toxicity if these are used with living organisms. So my project is taking this inherent wrapped chain end and converting it to a bromine. And this will not only make further modifications easier, as I said before, but it will also fix the problems I just mentioned. And how we plan on doing this is going through a thiol intermediate, that is just the sulfur chain end is a thiol. And the first reaction shown is known, and the second reaction is what is unknown. So we will be optimizing this. And how we will do this is using model systems. And this is because polymers that are commercially bought can be expensive, but you can make them But if you are spending days making this material, you don't necessarily want to use it in optimization reactions that may not work. So we are using MARC systems that are simpler, cheaper, more efficient to use. And the first one is dodecane thiol. This is what is called a primary thiol, because the carbon it is attached to is only attached to one other carbon. So this is extremely easy to attack and substitute for other groups such as bromine. And this makes it easy to see what does work, what doesn't work. And then we moved on to our second model system, adamantane thiol, which is a tertiary thiol. And this is more representative of what polymers are. Because polymers tend to have other functional groups hanging off of them or other side chains, this again represents polymers and is more close to the system we are using. But how we do this is we take our reactants, we take our thiol, our base, in this case triethylamine, and our brominating agent, triphenylphosphine dibromide. We put them in a vial, put it under an inert atmosphere because the oxygen in the air can react with our reagents and essentially stop the reaction from happening. And then we put this on a stir plate. If we are using elevated temperatures, we use a heating block and then we let it sit overnight to fully react. And then in the morning we come back and we need to purify our product. And we use two methods, and these methods depend on the size of the polymer and the solubility. And the first one is dialysis, and this is taking our reaction, putting it in a membrane that has holes of different sizes, and everything smaller than those holes will diffuse out into the dilute solvent. And then in the end you get more purified product as shown here, and you can do this multiple times to purify your product. And the second option is precipitation, and that is again taking your reaction vial, putting it into a solvent that your polymer is not soluble in, but everything else is. So your polymer comes crashing out and you can purify it that way. But in the end, whatever method you use, you need to remove the solvent, and we're aiming to get purified product. And how we analyze this is on nuclear magnetic spectroscopy, resonance spectroscopy, or NMR. And it has been explained today, but it takes advantages of the magnetic properties, and in my case, it takes advantage of the magnetic properties of hydrogen. And they give you a signal, and these signals can shift depending on what the hydrogen is next to. So if it's next to a bromine, the signal will be in a different place than if it's next to a sulfur. So you can see if your chain end has been modified. And what this looks like is taking our first model system, dodecane thiol, and you can see the hydrogen corresponding to the hydrogen here. In the starting material, it's quite prominent, and then as the reaction goes to full conversion, it disappears. And then the hydrogen corresponding here, it is non-existent in our starting material, and then it emerges as the reaction goes to full conversion. So we use this to try different conditions, and we change the equivalence of reactants, the solvents, the inert atmosphere, and we came out with these conditions where we get 3 equivalents of our brominating agent, 3 equivalents of our base, our solvent is DCM, sparged with argon at room temperature. So we moved ahead with these and went to our more complicated model system, adamantane thiol, and you can again see the peaks corresponding to these hydrogens here. They are very prominent in the starting material and disappear as it goes to 100% conversion. And then the peaks corresponding to the hydrogens in our product again emerge. And using this, we saw that anything above 5 equivalents for our brominating agent and our base does get us to full conversion. However, at room temperature, it also is at very high conversion, and if you leave it longer, it will push to full conversion. And so we went with room temperature because it's more energy efficient. And we moved on to actually doing it on our polymer systems. And the first system is polystyrene. This work was done by Ewan Lee in the Hawker Materials Research Group. And he first started by taking the RAF chain end, converting it to a thiol, and then taking that thiol and converting it to a bromine. And he did see bromination, however, he also saw an undesired product, the elimination product, in which you get a double bond here. And we are aiming for full conversion because these two products can be hard to purify from each other. So this system needs more optimization. And the system I'm working on is polymethyl acrylate. And again, I took the wrap chain end, converted it to a thiol, and from that thiol, I attempted to get the bromine, and I did see bromination. However, it was not in full conversion, and again, we are aiming for full conversion. So the further work is to optimize these systems, try different solvents. We saw that elevated temperatures do increase the rate of reaction. Try extra equivalents, and possibly, if necessary, try different brominating agents. And with that, I would like to thank the Reed Deolani's group, especially my mentor Emery, and the MARC program for funding my research. Thank you. Any questions? No? Okay.
On one of your NMR charts, this is just like something I'm curious about. It looked like the peak was the earlier one of the two in the simpler model. So that one, it looks like the middle peak and also the left are split into multiple different peaks. What causes that?
The splitting is due to different hydrogens. So these hydrogens here are split by these hydrogens, and they're because they're not equivalent, so you see splitting.